Good evening, everyone. Welcome to the week 12 live interaction session for the course Renewable Energy Engineering, Solar, Wind, and Biomass Energy Systems. So, let's just wait for a few minutes before we start our session for today. And I hope I'm audible. Thank you. So, let's just begin our session for the day. Let me just present my screen. I hope my presentation is visible to all. Can anybody confirm whether my presentation is visible and I am audible? Oh, okay. Sure. Thank you so much. So, I welcome you all to the week 12 and the last live interaction session for the course Renewable Energy Engineering, Solar, Wind, and Biomass Energy Systems. Myself, Pratyumnan, is the course team member responsible for conducting the live interaction session every week. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati, under the NPTEL program. So, in the last week, we discussed about the wind theory. So, we mainly focused on the concepts of wind theory, how the wind energy is used as a renewable energy resource, how the wind energy generation happens, how the solar energy is an indirect mode for the generation of the wind energy. And then we discussed in the lecture videos, if you see, there has been an extensive discussion on the different types of windmills, and then even on the different type of the wind speed at different coastal regions. So how does your wind speed varies with the different regions within India as well as in the world? So that has been discussed. and then we saw through the uh, different types of wind turbines, your horizontal axis wind turbines, HAWT, it is also, I mean, the abbreviation, and the vertical axis wind turbines. And then we saw the differences, its different types, and then uh, about the blades containing the airfoil. We saw about the uh, different dimensions of the airfoil, your chord length, your leading edge, trailing edge, and then we talked about the lift force as well as drag force, and then we discussed about the flow turning principle and the Bernoulli's theorem, and then we moved on towards finding out the amount of power that is available in the wind. How does the kinetic energy of your wind is extracted as the wind energy power, and then we discussed about the Betz limit. So before discussing about the the Betz limit, we discussed about three different parameters. I hope you will be able to recollect. One was the cut-in speed, rated speed, and cutout speed. So after which we discussed about the Betz limit, which was proposed by Betz. So that describes the maximum theoretical power that can be generated by a windmill. So it was calculated around 59%, and then we discussed on how Betz proposed that or compared the rotor as an actuated disk model and used the linear momentum theorem uh, propose the value of Cp, your power coefficient, as 16 by 27 or 0.59 or 59%, and then we also solve some of the numerical problems related to the wind energy concepts. So today, in continuation with the week 11 lecture, we will solve some of the problems, and also we will learn about more different parameters or the different terms that is involved in this wind energy concepts and theories. So the wind rotor characteristics. So the windmill has blades. So the blades basically have airfoil. So last week also we saw this diagram, but over there the diagram was pretty not clear. So in today's lecture, I hope this will be a more clear picture for you guys. So this is the airfoil. So the airfoil has a leading edge as well as a trailing edge. The wider part, if you see on the left hand side, is nothing but is your leading edge, and then the part towards the right hand side or the end of the airfoil is nothing but is your trailing edge. So the line that runs across the airfoil is nothing but is called as a chord, and then you have two different type of forces that is acting on your chord or the airfoil. One is nothing but is your lift force, and then the another one is nothing but your drag force. So the drag force, if you see the direction of the airflow and the drag force, they both are parallel to each other. So in case of the drag force, the direction of the force will be parallel to your direction of the airflow, and the major reason why this drag force arises is because of the viscous force on the surface of the blade and the unequal pressure differences between the surface. So this is about the drag force, and this is the expression. So D is nothing but it's equal to CD by half of rho A times V square. So here CD is nothing but is your drag coefficient. CD is your drag coefficient, and rho A is nothing but is the density of the air. Let me just zoom in. A is nothing but it's the projected area of the airfoil, and V is nothing but it's your free stream velocity or the undisturbed airflow. free stream air velocity, or in simple terms you can say it as undisturbed air, the speed of air, undisturbed speed of air. So this is about the drag force. So the drag force is a force that acts in a direction parallel to your airflow. So the one that acts perpendicular to your airflow, if you see, the lift is the lift force. So if you see, the airflow is along the I hope you are able to see the PPT. So the airflow is along this along the direction making an angle alpha with the chord. So this is the direction of airflow, and the lift force is perpendicular to your airflow. So that is what the force component that acts perpendicular to your airflow is called as the lift force. And the major reason why the lift force is generated is again the same, is because of the unequal pressure differences between the surface. The reason why there is an unequal pressure difference is basically because of the fact that it is the airfoil is curved in shape. So the amount of pressure difference that is present at the top and the amount of pressure difference that is present at the bottom will be different. And the lift force, similar to that of the drag force, is expressed as CL times half of rho A times A V square. CL is called as the lift coefficient. And again, u is your free stream velocity or the undisturbed velocity of the air or speed of air. Rho A is your density of air, and A is nothing but is your projected area of the foil. Next you have what is called as a pitching moment. So the pitching moment is nothing but it's a force that acts in a direction perpendicular to your chord or to the axis of the airfoil. So, and this is actually expressed as Cm times half rho A square A V square C. So the Cm is the pitching coefficient. Oh, sorry. So Cm is nothing but it's called as the pitching coefficient. And here you have, if you see, you have an additional term. Let me just or let me just reduce the size. Here if you see, you have an additional term C. So C is nothing but it is actually the chord length. C is your chord length of that particular airfoil. So these are the three different parameters. After that you have one more parameter, which is nothing but it's called as the solidity. So solidity is actually represented by this term gamma. So the solidity is also expressed as the ratio of the blade area to the swept frontal area. So the swept frontal area is also can be termed as the area that is swept by your rotor. So when your windmill is rotating, so the blades will be rotating, so the area that is actually swept or covered by your rotor blades or covered by the blades of your rotor is nothing but is called as your swept frontal area, or in a simpler terms if you want to say, it is called as the swept area of the rotor. And this swept area of the rotor is different for different type of turbines. So let me just write that expression. So solidity is expressed as blade area divided by the swept frontal area, or the area swept by your rotor, swept frontal area. And this is expressed as NC NC times divided by pi into R. So this is the general formula for solidity. So here N, what is N? N is nothing but is their number of blades. C is what I told here, this, which is nothing but is the chord length. And pi, you know, R is nothing but is the radius of the rotor, the rotating part of your windmill. So this is what is the general expression. So if you want to really know like how you got this formula, so solidity is nothing but blade area. So blade area is nothing but it is the number of blade times the area of each blade, divided by the swept frontal area or area of the rotor. So your area of each blade, so your blade, as we said in the last in the lectures also, the area of a blade is nothing but so the blade actually consists of airfoil. So we need to get the area of the airfoil. So since the blade contains airfoil, so the area can be expressed as C, that is nothing but your chord length, times L, that is nothing but your span length. So what is the length of the blade? So that so if you multiply these two, you will get the area of the blade. If you see in the video lectures also, there is a clear cut description of how of the projected area of the blade as C times L. So over there what they have done is they have taken a blade, and then each blade is divided into smaller sections. So the airfoil, when you see it from top and when they are divided into small section, each of the airfoil will look like rectangular in shape. So the area of the rectangle is nothing but it's the chord length, it's the length of the chord times the length of that smaller section. So if you integrate that across the entire area of the blade, you will get it as C times L. So this is the area of each blade, or R I will write. So then solidity is nothing but N times C times R divided by your area of the rotor is, since it's in circular motion, so the area will be pi r square times R times R. So this R and R will get cancelled, and you will get solidity as NC by pi r. But this comes with an assumption that your blade length should be equal to tip radius. So here I have written R, right? So I have taken the blade length is equal to the tip radius. So that is an assumption. It's not necessary that at all occasions your R and L will be same. So here we have assumed that the blade length is equal to tip radius. So otherwise you cannot write it as R. If you don't make that assumption, then you have to write this as L. So let me be clear here. So it will be C times L. Since we have this assumption, since it is assumed that the blade length is equal to tip radius, so the area of the blade can be written as area of one blade can be written as C times R. So this is how you actually get the formula for solidity. And this also varies depending upon the type of windmill that you actually use. So this formula is only for the horizontal axis wind turbine. So suppose if you want a vertical axis wind turbine, then the formula will be different. So in that case, so I'll just write this is for horizontal axis wind turbine. Suppose if you want to take it in the case of a vertical axis wind turbine, it will be different. So in that case, the formula will be solidity is equal to NC by R or NC by 2R. So if you see this NC by R, this is only valid for the Darius type. If you remember, we have two different type of classification for the vertical axis wind turbine. One is the Darius type, and can you tell me what is the other type of vertical axis wind turbine that we discussed? There are two types. One is the Darius, and there is another one. What is that? What is the other one? Yes, anyone? Because these are main classification. Yeah, Solvenius. Sorry, Savonius. Yes. So this is for Savonius type. So that is correct. So this is for Savonius type. So if you see, the solidity actually depends here on the chord length and your tip radius as well as that of the end. So in case of the horizontal axis turbine, if you see, we actually discussed about two different types. One was the multi-bladed horizontal axis wind turbine, and another one was the propeller type. So if you see in the multi-bladed ones, you actually had as its name suggests, multi-bladed. So there were so many blades. So approximately there were about 12 to 20 blades, and each blade was having and then the rotor diameter was approximately 2 to 5 meter in diameter. Then the next one was your propeller type. So in case of the propeller type, if you see, the number of the blades was in the range of, if I am not wrong, I guess it was around 3 to 4 or 2 to 3, yeah, somewhere around 2 to 4 blades in case of the propeller type, and each one was having somewhere diameter much larger compared to your multi-bladed ones. Approximately, I guess it was around 80 or 100 meter in diameter. So when you have a multi-bladed horizontal axis wind turbine, so over there the value of N will be more, because N here represents the number of blades, right? So for multi-bladed system, N value will be more, so which means that it will have a high solidity. So okay, it has a high solidity. So what does it actually mean? So what it actually means is, as the number of blades increase, the area of the blade that interacts with your wind will increase. So this will help in starting your rotor very easily. So the major reason, the beneficiary reason for increasing the number of blades in your system, even though if you see the available power in the wind, that formula, I hope we have it here. Yeah, if you see this bottom P wind, it's rho A times V cube by 2. So rho will be constant, velocity will be constant, A will be is the area of the rotor, so that will be constant. So what is the use of increasing the number of blades? So when you increase the number of blades, what happens is, it helps in easy start of your system. So the torque, so as you increase the number of blades, the torque that will be acting within your systems will increase. So it will help in, there won't be any disturbance or there won't be any difficulty in starting your wind turbine. So that is one of the advantages of a multi-bladed system. So by increasing, so what it means is, when you increase the number of blades, it has a high solidity, and that basically helps us in interacting. So that basically provides more area for your blades to interact with the wind, and that actually helps in the starting of your that provides enough torque to your system, and then it helps in starting of your windmill. So yeah, that is something that I wanted to say. And if you see, so let's just actually revise about these two different types of vertical axis wind turbine also. So I hope everybody knows the difference, or the reason, or the main what do you say, the main basis for the classification of the wind turbines. Horizontal axis is because the rotor axis is horizontal and is parallel to the direction of airflow. In case of the vertical axis, it is fixed, and then it is perpendicular to the direction of the airflow and vertical to the ground. So you have two types, one is the Darius and the Sovenius, as somebody rightly said. So the Darius type, they have airfoil sections, the blades are actually curved along the length, and then they have a high tip speed ratio. So here we have to discuss about another one parameter, which is called as the tip speed ratio. So since I said that the Darius type has a higher tip speed ratio, and Sovenius type, if you see, they have a lower tip speed ratio. So what is the definition for tip speed ratio? So tip speed ratio is nothing but, it is defined as the ratio of the speed of the blade tip to that of your free stream wind speed, or the undisturbed speed, undisturbed air velocity. So this is the tip speed ratio, and the formula is omega r times u, and this is represented as lambda, or let me just write it as tip speed. Tip speed ratio is omega r divided by u. So u is nothing but, it's a free stream wind speed or undisturbed airflow. Speed of the blade tip is written as omega times r. So omega is nothing but is your angular velocity. So it is not the velocity, it is the angular velocity. More so since the rotor is actually rotating, the blades are rotating, so you will have an angular velocity. Because of that only it actually rotates. So W is your angular velocity, and the R is nothing but the radius of the tip. So this is something about the tip speed ratio. So in case of the Darius type, this tip speed ratio will be very high, whereas the Sovenius type, the tip speed ratio will be very low in that case. And in case of the Darius type, if you see, the blades have a curved, the blades are actually curved along the length. And in case of the Sovenius type, if you see, it is a sliced hollow cylinder which is connected in S shape. So I hope you will be able to like get. So it will be somewhat like this. There is, yeah. This is 1S, and then the So it will be something like this with the airfoils that is actually present at the center. So this is designed for the souvenirs type. So yeah, that's something that we in the last class we were not able to discuss. Like we saw more towards your horizontal axis wind turbine, and we didn't see much on your vertical axis wind turbine. So yeah, I hope you won't have much doubt in that particular section now. So I hope there is no doubt. If you have any doubts related to what we just saw, drag force, lift force, pitching moment, or solidity, or the formula, you can just ask me now before we proceed towards the next section. Okay, so if nobody has doubt, then can I proceed with the remaining explanations? Do you guys have any doubt? So yeah, so let me just continue with my discussion, and in case if you have any doubts, then you're always welcome to interrupt me during the session. So last class, if you see, we talked about Betts limit, and then we also saw how to, like, what is actually the Betts limit. If you remember in the introduction session also, I said that it is actually the theoretical maximum amount of power that can be generated from the wind energy, and it was proposed out as the value was actually proposed out as 59% or 0.59. Let me just show that last live interaction session. So yeah, here we discussed the CP max value as 16/27 or 0.593. So this is actually the theoretical limit. The maximum theoretical amount of power that can be generated is 59% of the total power or the available power in your wind. So available power in your wind can be expressed as here rho 8 times V cube by 2, and last class we also derived how to calculate the power available in the wind from the kinetic energy of the air molecules or of the wind. From the kinetic energy of the wind, we derive the amount of power that can be that is available in the wind. I hope you remember how to derive. So yeah, we were discussing the Betts limit. So that was approximately 59% of the total power that is available in the wind. But Betts, when he proposed that, he took some of the assumptions into consideration. If you remember the linear momentum theory, so this is the 1D momentum, or to be very specific, the linear momentum theory. He first considered that the rotor, he compared the rotor with an actuator disk model, right? So and then based on this assumption or the comparison of your rotor as an actuator, or assuming your rotor as an actuator disk model, he used the linear momentum theory. And in this linear momentum theory, there were a lot of assumptions. So if you carefully see here, first assumption was that the airflow was supposed to be homogeneous, incompressible. I hope you remember what we discussed. The word incompressible means that the density does not vary as a function of time or as a function of temperature or pressure. Then we talked about the steady state fluid flow, where there is no variation of the flow of the fluid with respect to time. After that there were totally three different assumptions. One assumption was that they assume there will be infinite number of blades. Second assumption was a non-rotating wake formation in your airfoil. So as the wind passes through the airfoil, there are chances of the wake formation, and that wake formation can be in two different types. One is the non-rotating and another one is the rotating. So we assume that the wake that is actually formed in the air near to the airfoil section is non-rotating in nature. And third thing, which is not mentioned here, what we assume that was there will be no aerodynamic drag in the there will be no aerodynamic drag. But unfortunately these assumptions, so due to these assumptions you get the value of your Cp or Cp max as 0.593. But these are very ideal conditions. If you see in your practical applications, having an infinite number of blades is impossible, because for a multi-bladed system itself, if you see, we have only 12 to 20 blades. So infinite number of blades means that is actually not possible in practical situations. So when you have finite number of blades, so when there are infinite number of blades, the loss of energy, the tip loss, what is called, was actually neglected. But when there is a finite number of blades, the tip loss will come into picture, and we have assumed that there will be a non-rotating wake formed when the air flows through the airfoil. But that is not the case. Over there, whatever the wake that is formed is rotating in nature, and since there is a rotating wake behind the rotor, there will be an energy dissipation. So unless or until your wake is not rotating in nature, there will not be a much problem, there will not be much amount of energy dissipation. But once your wake starts rotating, due to that rotational motion, there will be some amount of the energy that will be lost. And we have assumed that there will be no aerodynamic drag that will be there in the system, but there will be a non-zero aerodynamic drag, because there will be some amount of the frictional force that will be acting on your rotor. So these are the three assumptions, and based on these three assumptions, we eliminated all the losses due to the wake, due to the blades, and due to the drag, and we proposed that the value will be 16 by 27, or 59% of the power available in the wind. But in the practical applications, as I said, this is not possible. So when you start including all these losses, the amount of power that you can derive from the wind will decrease. So and moreover, there are also other parts that is available. If you see, you have something called as a crankshaft, gearbox, transmission. So due to all those components that is present in your windmill, those also will add or contribute to these losses. So those minor losses from the different equipments in or the different parts in your windmill, and due to this different type of losses due to the wake formation, blades, and then the drag, your performance or the amount of energy that you can harness from the wind will decrease substantially, and the value will be somewhere around 30 to 40%, or 20, you can say 30-35% only. It won't be 59% as what you actually saw. So we have to actually account for these losses also. So for that, we relate the overall efficiency with your mechanical efficiency. So that's what is given here. Your overall efficiency is nothing but P out divided by half of rho A into U cube. So this is also called as Cp, but this Cp you have to multiply this Cp with the mechanical efficiency of the rotor or the turbine. Then only you will be able to accommodate for all the losses. So that's how you write efficiency of, or the overall efficiency is nothing but the mechanical efficiency times the Cp value. What is Cp? Cp is nothing but we last class also we discussed. Cp is nothing but it's called as your power coefficient or wind turbine rotor performance. More specific, if you want to say, it will be power coefficient. This is the right term, power coefficient. Let me just remove. So the wind turbine rotor performance is characterized by your power coefficient. So this is power coefficient. So Cp, so this is actually defined. If you remember last class also we saw the definition. The value of Cp is defined as the ratio of the actual power that is delivered by your rotor to the amount of power or that is available in your wind. So the power available in the wind, from the kinetic energy expression we derived it as half rho A times V cube. P out or P rotor we don't know, and if you use the linear momentum theorem, then we got the value of P out or the P that can be harnessed as nothing but rho A V cube by 2 into 4A times 1 minus A square. So can anybody tell me what does this value or what does A actually signifies? There was a special term for this. Last class we discussed, we devised this term in the linear momentum theorem. What is A? Yes, anyone? What is the what? How did we define the term A in the last session? Or what is actually, we have a specific name for this value of A, or this A symbol or expression. What is the value of A? And here okay, before that, here this V is nothing but U, and that U is nothing but your wind speed or your free stream velocity. So what is the value of A? I mean, what do you mean by A? So A, if you remember in the linear momentum theorem, when we were deriving, or if you see in the lecture, there is a detailed derivation of like from the beginning till the end of calculating the value of P out in terms of A and the thrust also in terms of A. So A we defined as a parameter. I'll just write the expression, then I hope you will be able to remember. A is nothing but U1 minus U2 divided by U1. So we got this expression, and then in order to simplify our equation, we described this u1 minus u2 by u1 as A. So here what actually A means is nothing but it has a special term called axial induction factor. So I hope you will be able to remember in the last session we saw axial induction factor u1 minus u2 by u1. So u1 here is nothing but it's called as, it is the free stream velocity, and your u2 is nothing but the upstream velocity at the rotor. So I hope you will be able to see this picture. So the actuator disc is at the middle, so that is nothing but it's actually a rotor, and then we have considered a control volume, or in simple words the place where we want to do our analysis. So here there is a flow of air, and here and at the end also there is a flow of air at 0.4, and both these flows are actually at the ambient pressure, so their velocity will be same as that of your free stream velocity. And V2 and V3 is nothing but the upstream velocity of the air, and V3 is nothing but the downstream velocity of the air. So V1 is nothing but is your free stream velocity, and your u2 is nothing but the upstream velocity. And your u2 upstream velocity at the rotor. So the rotor is actually placed in the points 2 and 3 if you see. So that is the reason we write upstream velocity at the rotor. So it's the axial induction factor. So the axial induction factor is also what it actually signifies is when the wind actually comes and interacts with the blade, how much does the velocity of the wind is actually reduce. So that is quantified by your axial induction factor. So here it's actually small a. A is nothing but axial induction factor. So it actually, as I'm repeating once again, axial induction factor is defined or is signifies the amount of velocity or the speed of the wind that gets reduced when the wind actually interacts with your blade. So this is about the axial induction factor. So if you see the value of power coefficient, P out by P win, so that is equal to 4A times 1 minus A, the whole square. And thrust coefficient is nothing but is defined as the ratio of the actual thrust that is experienced by your rotor due to the wind to that of your theoretical thrust. So the theoretical thrust will be nothing but half rho times A times V square. Again, V is your free stream velocity, and your actual thrust that is experienced by the rotor is nothing but this theoretical thrust times 4A into 1 minus A. So if you for easy remembrance, you can make it out like, you can do keep in mind this one. So Cp is nothing but 4A times 1 minus A, the whole square, and Ct is nothing but 4 just a second. Ct, that is your thrust coefficient, can be expressed as 4A times 1 minus A. So I hope you will be able to calculate the Cp max. So for Cp max, what you do is you take the derivative and then equate it, and then equate the expression to 0. From there you will get the values of A, and then you substitute, and then you can calculate the value of Cp. So I hope you will be knowing this, but let me just do that also once. It's just that, so that you know, if you have some confusion, then it will be helpful for you to clarify it. So if you have any doubts, then please uh, you know unmute yourself and interrupt me wherever you find it difficult to understand. So yeah, so Cp will be nothing but, I guess last time also we did this, but it won't take much time. 4a times 1 minus 8 times whole square. So if you take the derivative of this, then you will be getting 4a. So you can either apply the product rule, or you can just expand the square term. So let me do that, because that will be most easiest way. And then if you do dCp by dx, then you will be getting the expression as 3a square minus 4a plus 1 equal to, so this will be your expression for dCp by dx. I'll just write the entire process. So now you are expanding the bracket, so it will be 4a plus 4a cube minus 8a square. So if you take dCp by dx, the derivative with respect to a, if you take the derivative of Cp with respect to a, then you get 4 plus 12a square minus 16a. So this you have to actually equate it to 0. So you can write it as 12a square minus 16a plus 4 equal to 0. So that will be 3a square minus 4a plus 1 equal to 0. So that means you'll get, you can simplify this as 3a times 3a minus 1 times a minus 1 equal to 0. So the value of a will be either 1 or 1 by 3. But if you put the value of a equal to 1 in the expression, if you just substitute and check, then you will be getting the value of Cp as 0 if a is 1, right? So that means what? You cannot derive any power from the rotor or the windmill. So that doesn't, so then there is no point of doing that, right? So if you substitute the value of a as 1 by 3, you will be getting the Cp value as nothing but 4 times 1 by 3 into 1 minus 1 by 3, that is nothing but 2 by 3 times whole square. So if you calculate 2 by 3 whole square is nothing but 4 by 9. So 4 by 3 times 4 by 9 is nothing but 16 by 27, and that value will be around 0.59 something. So this is the value of Cp or Cp max. Honestly, similarly you can calculate the value of Ct max same way. So you just need to substitute the value of 1 by 3, or you can also state this as a thrust coefficient at maximum power, maximum theoretical power. In that case, your thrust coefficient will be nothing but Ct equals 4 times 1 by 3 times 2 by 3. So that will be nothing but 8 by 9. So 8 by 9 is around 0.889, I guess. Yeah. So from that point you can actually calculate what will be your Cp max that is nothing but your bets limit, and from that, from knowing your Cp max, you can calculate the value of Ct. Next we have a expression or a term which is nothing but it's the torque, that is at the maximum efficiency. So you have a particular rotor which is actually rotating at a particular speed, and then you are able so that speed actually delivers the most amount of power or the maximum power. So you can have a maximum, so that torque at the maximum efficiency, it's actually represented as 2 times rho times d times v cube by 27n. So once when we solve a question related to this, at that time we will see how to derive this torque at maximum efficiency. It's a very simple derivation. So after that we actually move on towards understanding some of the statistical models for the velocity distribution. So if you see, you actually need to calculate the wind speed. So here we have assumed the wind speed as 10 meter per second, or last time in the numericals also, as you remember, we stated the wind speed as 10 meter per second or 20 meter per second or some 35 kilometer per hour. But how do you actually get the value of the wind speed? So for that, usually this value is obtained in the meteorological department. So they use a device called as anemometer, anemometer. It's a rotating cup anemometer. So that actually calculates your wind speed as well as that of your direction. So from there you can actually get the speed of the wind, or the exact speed at which your wind blows. But since the wind do not flow always in the same way due to various kind of seasonal, due to the variation in the season, and then many other different factors, the speed of the wind will change. So in order to calculate the wind speed at a particular location and at a particular time, we actually develop models. So the statistical models are usually proposed, which helps us in getting to know about the wind speed or the probability distribution of the wind speed. So we usually use two different type of probability distribution model. One model is nothing but is your Weibull distribution, and another probability distribution model is nothing but is your Rayleigh distribution. So these are the two models. So based on these two probability distribution model, we will be able to calculate the average wind speed of that particular location on that particular time or that particular day. So if you see here, we have two different expressions for both the Weibull as well as Rayleigh distribution. So the small f of v, if you see, is called as the probability density function, and capital F of v is nothing but the cumulative probability density function. So let me just mention that. So f of v, small f of v, is nothing but probability density function. So this is similar to both your Weibull and your Rayleigh distribution, and capital f of v is nothing but the cumulative probability density function. Cumulative function, let me just write. So small f of v is your probability density function. So what it actually gives is nothing but is the fraction of time for which the wind speed is at a given velocity. So the wind is blowing at a particular velocity, let's say v naught. So for what amount of time will this wind blow at a speed of v naught is given by your probability density function, and the cumulative one of that, what it actually means is that nothing but is the fraction of time that the wind velocity is equal or lower than that of your v naught. So at every instant of time, at every instant of your particular velocity, you calculate the amount of time, or for this period of time the wind velocity is v. So that is given by your probability density function, and the cumulative ones is for the entire time, or it's like the addition of time for which your velocity was lesser or equal to this v. So that is called as the cumulative one. So you keep adding up the time for all the velocities which is equal or less than that of your v. So that is usually given by your so that is the capital F of v. So the values, if you see here, the k as well as that c, if you see in this variable distribution, is nothing but it is actually called as k is nothing but the shape factor, and c is nothing but is your scale factor. So these two factors basically determines or defines the uniformity in the wind. And among these two, the most accurate model, if you see, is the variable distribution. Of course, this variable distribution also deviates. This model also has a certain deviation from the experimental observation, and that deviation happens during the calm period. So the variable distribution also deviates, and that deviation happens during the calm period. Deviation in the variable distribution happens during calm period. So calm period is nothing but is the period at which the wind the speed of the wind is 0. So that period is called as a calm period. And the Rayleigh distribution is one of the most simplest one. Here the Vm is nothing but is the mean speed of the wind. And then so once you know the statistical models, then we move towards the calculating your average machine power or the average machine power of the turbine. So that is expressed as PW bar. So whenever there is an average, we usually represent it as bar. At the top we give a line, a dash is there. So that actually represents the average of that particular variable or that parameter. So that is nothing but it's equal to integral PW, that is the power of your wind, into PU du, and this integral is between 0 to infinity. So you have to solve this integral. So for that solving, you use the Rayleigh velocity distribution, that is this one, pi by 2 v by vm square into e power minus pi by 4 v by vm the whole square, and then you use the Betz limit 16 by 27, and then you get the average machine power as rho times 2 by 3 d square times u cube. So rho is the density, d is nothing but is the diameter of the rotor, and u is nothing but is your free stream velocity. So yes, now we can actually move on towards solving the question. So before that, in case if you have any doubts, then do let me know before we start solving the problem. Yes, anybody has any doubts? Because if you see this velocity distribution models, these are quite complicated, and uh, also, I mean, it's difficult to remember also. So if you have any doubts, then do let me know. But majoritively you may not require to really, like, what do you say, know how to solve. It's actually more towards knowing how the formula, knowing the formula, and how you actually apply the formula. If you know these two, then I hope it won't be of much trouble. So okay, if no doubts are then let's just go towards solving the first problem of this live interaction session. This is very similar to what we solved in the last session. So here they are asking you to calculate the total power of your wind stream, the total power available in your wind stream, and they have given you the specification, that is nothing but the wind is actually blowing at flows at a velocity of 2 meter per second in a location where the standard atmospheric pressure is 1 atmosphere and the temperature is 25 degrees Celsius. They are asking you to calculate the total power that is available in the wind stream. Here they have not given you the area, so let me just give. So area of the rotor is nothing but, you can approximately take it as 15 meters square. Oh, it will be more than that. Let's take the area of the rotor as around 200 meters square. So you are actually asked to calculate the oh yeah, okay, yeah, fine, yeah, okay, I didn't actually see this. So then this is not actually required. So area of the rotor will not be required, since this total power of the wind stream is actually, they are asking you to express it in terms of kilowatt per meter square. So area of the rotor will not be required. Now you are asked to so you are supposed to calculate the power available in the wind stream. So this is very similar to what we actually solved in the last class. It's just that the density is not given and you are supposed to calculate the density. And we also saw how to calculate the density, the expressions in our last class. So I hope you will be able to solve and then let me know the answer. Yes, how much? 5.172 kilowatt per meter square. Oh, and what did you get the value of density as? Okay, so you didn't, you actually took the value and then did. Okay, but there is also a way to actually calculate the density. Yeah, you can actually take that and do, but it's actually like last time, if you remember, we discussed P is nothing but rho m by RT. So since here it's actually given in 25 degrees Celsius, so it will be easier. But if suppose, let's say, the temperature was in 35 or 45 degrees Celsius, then you are supposed to use Pm by RT and then get the value. So your P is nothing but the pressure. Yeah, so 1 atmospheric pressure is nothing but 10 power 5 pascals, and then you have to uh, what do you say, m is nothing but, let me just write that, so 1.01325 times 10 power 5. So this will be your P, because standard atmospheric pressure, and m will be nothing but is your molar mass. So molar mass of air, I hope you can take it here as 28.84 kg per kilomole. So I hope you remember how to calculate the molar mass of air from our hydrocarbon discussion. So over there also, we, for burning of our biomass, we actually we were supposed to calculate the molar mass of air. So over there we took 79 percentage of the nitrogen and 21 percentage of the oxygen, and from there we calculated, or you can take it as 8.314, and temperature is nothing but 298 Kelvin. So okay, let's take for the time being rho value as, what rho value did you take? 1.293. I guess somebody, what was the rho value that you took for solving your question? Okay, yeah, so okay, let me just solve it with respect to that, since one of the members have solved it, so we will use that also, that itself as a ratio, and then let's calculate. So P win will be nothing but half rho A times V cube, and since your they are asking you to calculate the power of the wind stream in kilowatt per meter square, so it will be P wind by A, that is nothing but 0.5 times rho times V cube. So P wind by A is nothing but 0.5 times rho is nothing but 1.293 that was taken, and then velocity is nothing but 2 cube is nothing but 8. So yeah, 5.172, but here the thing is it in terms of watts or kilowatts? Now, since the density is in kg, it will be in watts, because 1 watt is nothing but 1 joule per second, and so yeah. So this will be nothing but, it will be expressed as P wind by A if you take it in terms of in terms of kilowatt per meter square hour. If they want you to express, then it will be some very small value. Yeah. So this will be your answer, 0.005172 kilowatt per meter square. Again, if suppose if your value is going to be different, the temperature and the pressure, then you are supposed to calculate the value of density, in case if it is not given in the question. If it is given in the question, then I think you are lucky enough to just use that value and solve it. But if it is not given, then you need to calculate using P is rho is nothing but Pm by RT, and from there you will be able to calculate. And so I hope you know how this rho by P rho is equal to Pm by RT comes. Let me just quickly brief that. So PV is nothing but it's equal to nRT from the ideal gas law, and N is nothing but mass by molar mass. So if you take the volume from your right hand side to the left hand side, from your left hand side to the right hand side, so it will be P equals M RT by capital M times V. So M by V is nothing but it is density. So P is equal to rho times R times T by M. So then if you can, then you can express this as rho as Pm by RT. So yeah, this we did it in the last class also. It's just a very quick recap. So let's move on to next question. So next question is about something on tip speed and rotational speed of the rotor. So here you have a 30-meter diameter 3-bladed wind turbine, which basically produces a power of 800 kilowatts at a wind speed of 14 meter per second. The density of the air is 1.225 kg per meter cube. They are asking you to calculate the rotational speed of the rotor if the tip speed ratio is 4, and what is the tip speed ratio. So how to solve this? Omega R by, that is tip speed. Okay. Okay. R, so you have to take that that as your so 30 meter is the diameter, R is here is radius. So yeah. I do not have an answer. I am also supposed to solve it here in front of you guys. So let me just start solving. So can you just direct me how did you go about, like how did you calculate the rotational speed? Yes. Okay. Then 4 into 14 by 15, yes. But okay, yeah, yes, that's fine. Mm. So they are asking you the rotational speed, so that will be your hmm. Okay. Let me let yeah, fine, fine. So rotational speed is nothing but it is your omega. I mean the angular velocity. So that is the one. So here we know the tip speed ratio is nothing but it is equal to your 4. So that is given. So that will be nothing but it's omega r divided by u. So u is nothing but it's your free stream velocity, and that is given as 14. So you know what is, yes, you need to calculate omega. So it is tip speed ratio, that is 4 times u divided by r. So r is nothing but is the radius of the rotor, and that is nothing but, so it's actually 30 meter in diameter, so 15 meter will be the radius, and u is nothing but the free stream velocity. So that will be 14 meter per second. So omega will be nothing but 4 times 14 divided by 15. So let's just calculate. 4 times 14 will be 56 by 15, 3.733 3 rpm, that is rotations per minute. Now here you need to calculate the, let us take this as a tip speed ratio. So hmm. So here you are asked to calculate the tip speed ratio. Now let's calculate the tip speed ratio itself. So in that case, how will you calculate the tip speed ratio? You cannot take that omega as 3.733, but because that is something which is like, what do you say, confined to the problem A. So here we are just asking you to calculate the tip speed ratio. So in this case, how do you calculate? Your r and u will remain the same. So you are supposed to calculate the value of omega. That is nothing but your rotational speed. So rotational speed can also be defined as the amount of rotation or the number of rotations per minute, right? That's what is rpm. So value of omega can be expressed as the amount of area that your this thing covers per minute. Oh, sorry, per second. So can you write it this way? 2 pi times n by 60. So if you do that, I mean, sorry, n is r here. so the area that is basically covered. So if you do that, you will be able to calculate the value of omega. So this, I guess this you will be able to do. Next we move on towards the next question. So here you are supposed to calculate the size of a wind turbine rotor, and that wind turbine rotor is approximately generating 250 kilowatt of electrical power, and it's actually rotating at a steady state, a steady wind with a speed of approximately 20 meter per second. They have asked you to assume air density is 1.225, Cp value is 16 by 27, and eta. So here this eta here, what is eta is the mechanical efficiency of your turbine. So that value is asked. So they have asked us to take that value as 0.75. So how do you calculate this? I mean, how to go proceed with this? Mm. 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 Yeah. So let's just calculate it. Yeah, anyway, that is the way how you actually solve it. So since we got this time, so yeah, let's just calculate. So but that is the way you could solve it. So we usually use this expression. So eta overall is nothing but, as we said, it's eta mech times Cp. And the reason why we did this is because if you see, in case of the mechanical efficiency, we are supposed to include all the different kind of losses that happens. It's the loss that is actually due to your different components that is present in the turbine, as well as due to the uh, drag, the rotation of the wake, and your the number of blades, the tip losses that happens. So we are supposed to include all those into your account to calculate the efficiency, because at the end of the day, that is what we are actually going to harness from the wind energy. So that is the reason there is a eta the mechanical efficiency of the turbine term, that eta mech, actually comes into picture. So let's use this expression. So eta overall is, so overall efficiency is equal to P, can be expressed as mechanical efficiency of the turbine times your Cp, and this overall efficiency can also be written as P out by P win. So P, that is power available in your wind, is equal to mechanical efficiency of your turbine times Cp. So the mechanical efficiency of the turbine here is given as 0.75. And the Cp value they are taking, they are assuming you to take it as 16 by 27. So the so P out or P that can be harnessed, or P that is what do you say, available in the rotor, P that can be drawn from the rotor, can be written as P win times mechanical efficiency of the turbine times your Cp. So P out is nothing but P win So P wind is so that is usually expressed, how you express P wind. P wind is nothing but 0.5 times rho times A times V cube. So you're just asked to substitute all those things. So P out is nothing but it is given as 250 kilowatt, and your rho, that is the density of the air, is taken as 1.225 kg per meter cube. So you can write this as P, or let's say better, you can write it as 250 kilowatt is equal to P wind, that is 0.5 times rho is density 1.225 times area. So that we do not have an idea, as said by one of you guys. So A is that is what we are supposed to calculate, times V cube. So V is nothing but the velocity of the wind, which is given as 20 cube. So this times mechanical efficiency of the turbine 0.75, and your Cp value is 16 by 27, or let me take it as 0.593. So from here you will calculate the area. So let's just calculate. But here if you see, the power that you are going to get out, or the electrical power, is expressed in terms of kilowatts, but what you will get from this expression, that is P wind times mechanical efficiency of the turbine times Cp, will be in terms of watts. So we need to express kilowatt in terms of watts, so that will be multiplied by 1000. So P out is 250 kilowatt, or 250,000 watts. So you are just so 20 into 20 into 20 will be 400 times 20, that will be 8,000 times 0.75 times 0.593. So area will be let's calculate 0.5 times 1.225 times 8,000 times 0.75 times 0.593, 2179.275, 2179.275. So area will be equal to So the area will be approximately 114.717 meter square. Now this is actually the area that you have calculated. You are supposed to calculate the size. So which means they are asking you to calculate the radius of the wind turbine rotor. So area will be nothing but, for a rotor it is circular, so it will be pi r square. So area of the rotor can be expressed as pi times r times r. So r is nothing but it's your radius of the rotor here. So then what it means is 114.717 is equal to pi times r times r. So r square will be equal to 114.717 divided by pi. So 36.5340 meter square. So the value of r will be nothing but the square root of this. So the radius will be 6.04 meter. So the radius of the rotor will be around 6 point, the radius of the rotor is 6.04 meter. I hope you also got the same value. Yeah, okay, yeah. So this is how you are supposed to calculate. This is a very simple question. So based on this, you can have a variety of model, like they can give you the density of the air, like similar expression. They can give you the area, they can give you the wind speed, they can give you the mechanical efficiency of the turbine, the value of the CP, and then they can ask you to calculate what amount of the electrical power will be generated from the system. So that can be one way of asking this particular question. Or they can, other way around, they can ask is that they can give all the parameters, the electrical power, the wind speed, the area, the density, and the CP value, and then they can ask you to calculate the mechanical efficiency of the turbine. Or they can ask you to calculate the wind speed. They can give you all the parameters except the wind speed, and they can ask you to calculate. So it's just about using this formula, that is nothing but overall efficiency is equal to the power that can be harnessed from the rotor to the power available in the rotor, which is nothing but it's equal to the mechanical efficiency of the turbine times the power coefficients. So using this expression, you can actually like play around. They can ask you to calculate any variable here. So let's solve one more similar problem of this kind. Over here we will be calculating the torque at the maximum efficiency. If you remember, we actually solved this problem, right? We actually saw this expression. Torque at maximum efficiency is nothing but 2 times rho times d times v cube by 27 times n. So let's just solve the same problem here. You can assume the number of blades. Assume number of blades to be 3. Number of blades to be 3. Or let me just put it as a separate question. So they are just asking you to calculate the the torque at maximum efficiency. Now calculate the torque at maximum efficiency. This is just for a practice. So now what will be your answer? So you have this expression. Let me just so you are just supposed to calculate the value of the torque at maximum efficiency. So you have the value of rho. Rho is nothing but is the density of your air. D, that we have actually calculated now. So we got the radius of the rotor as 6.04 meters. So then your radius of the rotor will be is 6.04 meter. So diameter will be this times 2, so it will be 12.08 meter. And n is nothing but the number of blades, so that is 3 here. I am assuming it as 3. So for this system, I am asking you to calculate what will be the torque at the maximum efficiency. It's simple, you just need to substitute in this equation, but for this I just want to actually show how you got this formula. So torque can be expressed as power divided by omega, double. So this can be written as power divided by pi dn, pi times d times n. So this power is nothing but the overall efficiency. So you are supposed to take the mechanical efficiency eta into account times your P total, that is whatever the P that is available in the wind, times Cp. So torque will be nothing but it will be equal to eta times Cp times P total, so that is power available in the wind. Oh, let me just write this as P wind. So P wind is nothing but 0.5 times rho times A times V cube So since this is at a maximum efficiency, we know that at theoretical maximum efficiency the value of Cp will be 16 by 27, right? So then just it's about what do you call substitution. So torque is nothing but times 16 by 27 times half times rho into A into V cube, the whole divided by pi times d times n. So here d is nothing but is the diameter of your rotor. So you are supposed to express A in terms of d. So area is nothing but pi r square. So that also can be expressed as pi d square by 4 into d square 4. So that I am writing here as 8. So this pi so pi will get cancelled, the d and d square will get cancelled, and there will be a d in the numerator, and this 8 will cancel with this 16 and it will be 2. So that's how you obtain the formula. So then torque will be nothing but 2 times rho times d times v cube whole divided by 27 times n. So what value did you get? I mean, did you solve this? Because it's just about substitution. So what is the value of the torque at maximum efficiency? So let's calculate that. So 2 times rho, the value of rho is 1.225 times d is 12.08 times v cube, v is nothing but 20, so 20 cube is, I am writing it as 8000 divided by 27 times the n is number of blades, so number of blades here is 3. So we are supposed to calculate this. So torque at maximum efficiency can be written as 2 times 1.225 times 12.08 times 8000, 236768 divided by 23 times 27 times 3 is 81. So this will be the torque, 2923.06, 2923.06. What will be the units of torque? So torque is expressed as Newton meter. So torque is nothing but it's the force times the distance f time r times f. So it's for force it is Newton, and for r or L, whatever that is a length parameter, so it will be Newton meter. So this is a kind of an example where they will ask you to calculate the torque at maximum efficiency. So yeah, I hope since we have derived this, now I hope you will be able to confidently solve this problem. In case if you find any difficulty, then do let me know now before we progress towards solving one question and then concluding the session for the day. Yes, any doubts? Yes, do you guys have any doubts? Based on that torque at maximum efficiency question that we discussed, or shall we proceed towards solving one more question? Okay, I guess there is no doubts, then we can proceed towards solving one more question. Yeah. So here you are asked to consider a wind turbine that is having a diameter 10 meter in dia, and then it is actually rotating at a speed of 15 meter per second. The velocity of the wind at that location is 130 r per minute, is nothing but it's the rotation per minute, so rpm. So this will be the angular velocity that is given to you, and the power coefficient at this point, your Cp value is given as 0.35. They are asking you to calculate the tip speed ratio and the torque coefficient, that is nothing but your Ct, and what will be the torque that will be available at the rotor shaft. Assume the density of the air to be 1.24 kg per meter cube. Here for your solving purpose, you require a relationship which is nothing but tip speed ratio. Apart from that, what do you say, it is defined as the ratio of the speed of the blade tip to the free stream wind speed. It can also be written as power coefficient by torque coefficient. So with this expression you will be able to comfortably solve this question. So here torque, actually if you see, it can be written as, it can be expressed as Ct times 0.5 times rho times A times U square. So first you need to calculate the value of A. So A is nothing but, since we have diameter, you can use pi d square by 4 or pi r square, so that's up to you. So since here it is given in terms of dia, I am going to take it in terms of dia, divided by 4. Oh sorry. So the value of A will be nothing but 78.5 meters square. So you know the value of A, angular velocity you know, that is, it is given as 130 rotations per minute. Now they are asking you to calculate the tip speed ratio. So that is nothing but, it's omega r by u. Omega is the angular velocity, r is nothing but it's the radius, and u is nothing but it's your free stream velocity. So 5 times angular velocity divided by 15, you'll be able to get the tip speed ratio. So you know the power coefficient as 0.35, right? So they are asking you to calculate the torque coefficient. So torque coefficient will be nothing but power coefficient by tip speed ratio. So that will be equal to what will be the tip speed ratio? It will be, so I mean you can calculate the tip speed ratio. So once you know the torque coefficient is nothing but it's the value of Ct. So it's just that after that you need to substitute. So torque will be equal to Ct once you calculate. .5, rho you know as 1.24, and A you know as 78.5, U is 15 meters square, so 15 times 15. So once you do this, you will be able to calculate torque as Newton meter. I mean, you can get the value of torque. So yes, so we have actually one more question to solve, but since we are actually running short of time, what we can do is we will be having a session tomorrow also. So that will be an extra live interaction session. The purpose of that session is actually to kind of solve more problems and conclude the session, as like on an overall basis we have to conclude the session. So we will be taking up with not just with this problem, we will be taking more problems in wind energy, and after that we will also revise through the solar energy and the biomass energy concepts. So yeah, that will be for today, for tomorrow. So tomorrow also we will be having a live interaction session, and that will be 1 minute. There is a question, what to do for our exam, is it final on 27th April? Yeah, like there is a person who has raised his hand. Yes, can you please unmute yourself and yeah, yeah. Yes, can you please be? I mean, I'm unable to hear you. Yeah, I guess. I mean, have the dates been given as 27th April? Oh, okay. Then in that case, you actually need to contact the NPTEL team only. You can actually email them because as teaching assistants, we do not have much, what do you say, clarity on the Swayam portal. They would have given an ID, right? So in that ID, yeah, 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 yeah. And somebody has raised their hand. I guess that person is not there in the queue. Yeah, tomorrow. Yeah, yeah, same timing, 5 to 7 p.m. Yeah, yeah. So okay, then if let me just stop presenting the screen. So yes, and then okay, yeah. So yes, week. Which week? Week 10. Was it not released? Like, oh, okay. I mean, okay. I will let you know that by tomorrow whether when will they release this because yeah. So I'll let you know tomorrow. But if you see in the I mean, Professor Vaibhav Vishant Gaut sir also took one live interaction session. So in that also he has solved, I guess, week 10 problem. Anyway, you can, yeah, you can actually see that, or I will also let you know tomorrow whether, like, when will they be uploading the solutions for week 10. Yeah, 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 yeah. Okay. Yes. Yeah. Okay. Okay, okay, okay. So since I actually don't, I'm not the person responsible for the solution, I will talk with both the instructors and I will let you know tomorrow. Yeah, actually, I guess for assignment 6 to 10 it was released, but for the first five it was not released, I think. Yeah, okay, yeah. Anyway, I will just contact both the instructors and then uh, I'll let you know. So, yeah. Actually, this will be a right question to discuss in the Q&A portal. If you see you do have a discussion forum, right? In the I would say it would be much better to write it there because over there the faculty, like, what do you say, the faculty members have a direct access to that so that they can read your comments and they can respond to you directly because I do not have much idea on what will be your exam pattern. So yes, if there are no more queries, then I think we can conclude our session. I can discuss till week 11 assignment questions because week 12 assignment questions answer key will be released only on 17th April if I'm not wrong. So till week 11, whatever doubts, if you have any doubts, then we will discuss those doubts till week 11. But week 12, I'm not allowed to discuss that before the answer key is released. So yeah, I am not bound to do that. So till week 11, if you have any doubts, then you are always welcome to bring it up here. Yeah, okay, yeah, sure. So let me just conclude the session for today. I thank both the instructors, Professor Vaibhavishan Gaut sir and Ananda Lakshmi ma'am, for providing me this opportunity to interact with you all in this Sunday afternoon. Tomorrow also we will be having a extra live interaction session from the same time, 5 p.m. to 7 p.m., and that will be the last live interaction session. I hope to see you all there. And in case if you don't have queries, then yeah, so happy learning and bye.